This video is part 2 of lecture on Section 5.2 from Math 311, course in linear algebra at Western Illinois University. Last time we talked about orthogonal complements, and now we're going to talk about orthogonal projections. So orthogonal, the projections that we're talking about are generalizations of the projection we had earlier when we projected one vector onto another vector. Okay, the main idea again is to we're going to find two. Given a subspace, we'd like to find we would like to find its orthogonal complement, which we did last time. But now we want to show that anything in Rn can be written as a sum of something in the subspace and something in its complement. So that's what we're going to start with. So suppose W is a subspace of Rn, and the question is we're going to start with is, given a vector V, can we find vector W in big W and vector P in W perp such that V is the sum of W and P? And the answer is an enthusiastic yes. Okay, now how do we do this? Certainly not quite. It's not obvious. And what's going to help us out is right now we're going to assume that W has an orthogonal basis. Remember, an orthogonal basis, this is just a set of orthogonal vectors. So all these vectors, we have U1 through UK. That's what, sorry for the bad penmanship here, these are supposed to be used. U1 through UK, where you take any two of these and they're orthogonal to each other. Okay. Now we will see in the next section that this is that every subspace has an orthogonal basis. It's not trivial at all, but right now we're just going to assume that W has an orthogonal basis. If it has one, then we can proceed as follows. What we're going to do is basically, if we have, we're going to take V and we're going to project it onto each vector in this orthogonal basis. Okay, so we're going to let W be the sum of all these projections. So we're going to let W be the projection of V onto W1 plus the projection of V onto W2 onto U2 and so on up to the projection of V onto UK. And if you remember the formula for projections, the projection is V dot U. In this case, it would be V dot U1 divided by U1 dot U1, this number times the vector U1 plus and so on. All right, and to simplify this, we're just going to let this quotient right here, we'll call that C1. This will be C2 and CK and so on. All right, and then we're going to let P just be the difference, V minus W. So if everything else works, we can see that we can just add W to both sides, and we'll see that W plus P is equal to V. All right, now why does this work? Okay, well, what we're going to do is we want to show that, well, what actually do we have to do? We want to show that, well, we clearly see that this little w, it has to be in big W because it's the linear combination of the basis elements. So we can say clearly, little w is in big W. Now we need to show the other thing. We need to show that P is we want to show that P is in W perp. Okay, so we have to show that P is going to be P is going to be in W perp. So what we can do is we're going to show that P is orthogonal to each element in its basis. All right, so let's first show that consider P dot U1. Okay, all right, so what is that going to be? That is going to be V minus C1 U1 minus C2 U2 minus dot 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 minus C K U K. Okay. Dot U1. Okay, now once we will just use the distributive property of the dot product, and this will be V, this should be a V dot U1 minus C1 U1 dot U1 minus C2 U2 dot U1 minus dot 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 minus CK UK dot U1. Okay. Now this is where we use the orthogonality comes in. Because this is orthogonal, we can see that this is going to be 0, this is going to be 0, and then all the other terms are in here are going to be 0. So we'll get this is just going to be V dot U1 minus C1 U1 dot U1. Okay. All right. But what is C1? We said that C1 is really just this. So this is V dot U1 minus V dot U1 over U1 dot U1 times U1 dot U1. Okay, so then this, now you can see what's going to happen. I think this number and this number cancel, and then we just V dot U1 minus V dot U1. So this is going to be 0. Okay, so we've got P dot U1 is going to be it's 0, so P is orthogonal to U1. Okay, and then similarly, P dot UI equals 0 for I equals from 2 to K. And I think the reason for that is you'll see that all of these things will be, all but one of the, you'll have V dot U sub I minus CI U sub I dot U sub I, and then everything else is going to be 0. And then if things cancel out, and you'll get 0 again. So, and then therefore, because P is going to be in, so P is orthogonal to all the generators of the subspace. So therefore, so by the last lecture, we get that P is in W perp. Okay. Now, not only that, but not only that, we get something even better. It turns out that W and P are unique. Okay. That they're uniquely determined. Okay. So why would that be? Well, if let's say we have two possible values of W and two values of P that work. So let's say that V is equal to W1 plus P1, and it's also equal to W2 plus P2. Okay, for some W1, W2 in W, and P1, P2 in W perp. From here, we can do a little rearranging. We can subtract W2 from both sides and P1 from both sides, and we'll get that W1 minus W2 is equal to P2 minus P1. Okay, after we just do a little linear algebra. And then this is in W because W is closed under vector addition, and similarly W perp is a subspace, so it's closed under vector addition. So this expression is going to be here, is going to be in W perp. Okay, but these are equal. Okay, whatever vector this is, it's in both V is in both W and W perp. But we know we proved last time that W and the intersection of W and W perp is 0. Okay, so because this is in W and W perp, which is we showed is 0, we get that W1 minus W2 is 0, and P2 minus P1 is 0. So that means W1 has to equal W2, and P1 has to equal P2. Okay, so not only we get W and P, but we've shown that they're unique. And what we've just proven is the orthogonal decomposition theorem. Okay, which says basically what we just said. If W is a subspace of Rn and V is a vector in Rn, then V can be written as W plus W perp, or little w plus little w perp, where little w is in big W and little w perp is in big W perp. I'm just using the notation from the book here. And where these, again, these are unique. And the nice thing about this is, so we've proven this big theorem, but as a nice corollary or a nice little consequence of this, we can now prove that W, the orthogonal complement of the orthogonal complement of W is W. We already know that W is contained in W perp perp. Okay. Now what we want to do is we want to show that the other direction holds. If we take something in here, we have something in W. So if V is in W perp perp, okay, then in particular we know that V, if we take well, V is going to have its own decomposition. Okay, so V is equal to little w plus little w perp for some w, for some little w in big W and little w perp in big W perp. Okay. Now what happens if we take the with the dot product with a W perp? And let's see what happens here. All right, so first off, and let me make sure we get this right here. 0 is going to be V dot W perp. And that's because by definition we're picking V to be in the orthogonal complement of W perp. Okay. All right, then we can replace V with W, little w plus little w perp. Okay. And you can use the distributive property of the dot product. Okay. And then because little w is in, this is in W, this is in W perp, this has to be 0. Okay. And so this is going to be the square of the length of W perp, right here. Okay. But we've just shown that that's 0, so that shows that W perp is 0. Okay. And if this is 0, then that means V is W. And little v is in W. Okay. All right. So this shows we started with V being in W perp perp, and we've shown that V is in W. So that means that this is contained in here, and we already know that W is contained in here. So that proves the corollary there. Okay. All right. All right. Let me conclude with this example here. I picked this one so it's not quite as nice as the examples you see in the book, and by not quite as nice, that means we have fractions, which we know how to deal with. We just have to be very careful and very patient. Okay. All right, so we've started off with a subspace, which is the span of these vectors 1, 1, 1, 1, negative 2, 1, and we'd like to find the orthogonal decomposition of V. So that's what we mean by this, the orthogonal decomposition. I should say that this is what we call the orthogonal decomposition of V with respect to W. Okay, so we would like to do that here. Okay, now you'll notice that I've given you a basis which is orthogonal. Okay, if you take the dot product of these two vectors, you get 0. So this is already an orthogonal basis, thankfully. Okay, so we can take this to be U1 and this to be U2. Okay, and then we can check that V dot U1 is, if you do this, this is 7 plus 6 plus 4, that is 17. U1 dot U1 is 3. V dot U2 is 7 minus 12 plus 4, which I think is negative 6, negative 1. And then U2 dot U2 is equal to 6, right? Because we have 1 squared plus 2 squared plus 1 squared. All right. All right, so we want to take 17 thirds times U1 plus negative 1/6 times U2. Okay, and then if we do the fractions very carefully, we can write 17 thirds is 34/6. So this will be, we take 34/6 minus 1/6, that's 33/6, which is 11 halves. Then we take 34/6 plus 1/3, which is 1/3 is 2/6, so this is going to be 36/6, or just 6. And then we have 34/6 minus 1/6, which again is 33/6, which is again 11 halves. Right? Okay. And then our W, if you will be 11 halves, 6, 11 halves, and then we want to subtract that from V. So V is still 7, 6, 4, and this is going to be 14. 14 minus 11 is 3 halves. 6 minus 6 is 0, off an easy calculation, and this will be 8. 8 minus 11 is 8 halves minus 11 halves is negative 3 halves. Okay. So we get that 7, 6, 4 can be written as 11 halves, 6, 11 halves, and plus 3 halves, 0, negative 3 halves. And you can check that these are you can check that this is going to be in W and that this is in W perp, and in fact these are orthogonal to each other. Okay, you can actually check. It's very easy to see these are orthogonal to each other. Okay, so that would be an example of an orthogonal decomposition where this is in W and this is W perp. You could also see that one thing here that we will prove a little later is the dimension of W and W perp have to be equal to the dimension of Rn, which is n. Okay, But we'll explore that and other things next time. Thank you.